So we have n binary or polar patterns, and we want to store it in some memory. And here you can see our patterns, and we are storing it into a memory. And we do that via an auto product. So we just multiply every pattern with itself. So xi is just one of those patterns. So it's the auto product. You can see that's the HAP rule. And so this matrix is of dimension d times d. And we have stored all these patterns into this memory. And then we want to retrieve some pattern. So for example, we get some incomplete pattern, it's noisy or something. And we want to retrieve the original out of this memory. So we plug it into a memory, and what our associative memory should give us is the original pattern. So it should associate the right pattern to our input. There is also a version, for example, that's hetero-associative. So for example, the input could be some melody, and you get the right image out of it, for example. So, and so probably you can see here why this was some model for neuroscience, because I think it's also in our brain something similar happens. So if you I don't know, hear someone whistling a song, then suddenly you have the whole song or a whole different memory in your mind. Yeah. And what actually happens here is that, so we plug in our pattern, and then we iterate this update rule. So this is the sign function. We multiply our pattern with our memory. Probably we add a bias, we apply the sign, and we iterate this. And at the end, at some point, this iteration should stop. So we should converge, and what the result should be our original pattern. And this iteration is governed by an energy function. So what we end up at the minimum of this energy function here. And it's actually a rather simple function. So it's just a quadratic form. And you can see here that the input pattern and ours, so we multiply, we build the inner product with our input pattern, with all of our stored patterns. And then we just square this inner product. And so here we only have -1 and 1s, or 0 and 1s. So this inner product just counts how many entries are the same, and then squares it. Yeah. So it's actually a very, very simple, neural network. And that's one of the easiest form, or the simplest form of a associative memory. So to integrate associative memory into deep learning, we would like to store a lot of those patterns. So one reason could be we want to do, for example, a reinforcement learning, and we have a lot of situations that could be those incomplete data or noisy data, but we only have a few actions, and we know that every time I meet a door and there is something else happening, I want to perform this action, and so I could store prototypes of such actions here. And every time I get the pattern, I probably perform this action. Or I could associate with a hetero-associative memory. I could associate various things. So for example, here I have a representation of a complex scene. I don't know, there is a fork, a table, and something else. So associated with the action food or eating or something. I don't know. But this only works if we can store a lot of such patterns. We want to retrieve this pattern in one update step, because so we want to equip a neural network layer with associative memory. So we don't want to iterate inside of this memory, inside of this layer. And we want it to be differentiable to perform gradient descent. So the last 2 points, we already have a problem with our traditional Hopfield network. We need to iterate to retrieve the pattern, and of course it's not differentiable. We have the sign function and binary patterns or polar patterns. So what is with so how many patterns could such an Hopfield network store? And this is one reason why after the 80s nobody was interested anymore. Not many. So we have the storage capacity C, and if we permit a small percentage of error when retrieving, it can store 0.14 times D times the dimension patterns. So let's say we have polar or binary images of dimension 64 times 64. Then this would be 570 patterns. The problem is now if they are highly correlated, it's much less. And you can see that here we have an experiment where we have 6 images. We try to we store them in a traditional Hopfield network. We try to retrieve HUMA, and what we get is, I don't know what, some mixture of all these patterns. So such a standard Hopfield network is really useless for our case. Small storage capacity, not differentiable, and it doesn't. We have retrieval in multiple update steps. So the question is, are we done yet? And the answer is no. In 2016, Hopfield and Krotov published a new paper. So that's the same Hopfield that came up with those Hopfield networks in the 80s. In 2016, and now he's way in his 80s and is still publishing papers. They introduced modern Hopfield networks. And if you remember, here we had a quadratic interaction between patterns and stored patterns. So input pattern and stored patterns. And so now they have actually a very simple trick. They say, okay, we just have an interaction function. And instead of squaring it, we just have a higher order polynomial. So for example, A can be 2 or 3 or 4 or whatever. And this turns out to increase the capacity massively. So here you can see a plot with the dimensions and the storage capacity. And here blue is the original, the 0.14 times D. So it's just linear. And here we start to really get quite significant growth. So that sounds good. Suddenly we can store a lot of patterns. 1 year later, there was I think it's a French group, so the Mirzigil et al. They said, yeah, well, why not just make the interaction function the exponent? And turns out then we get exponential growth in capacity. So this is, you can see here in this plot, so this is now our new capacity. This is the capacity, for example, with A equals 4. So seems as if the storage part is fixed. Do we have any downsides? And yes, there is a big downside actually. If you remember the energy function, if we write the energy function out so of the original Hopfield network, it's just Xi times the outer product of our X's times Xi. So we only have this storage matrix inside. But if this interaction function, if we don't only square anymore, we don't just get such a nice matrix, a D times D matrix where we can store everything. We really have to store the original patterns. So instead of, so this is really, it doesn't depend on the number of patterns. So n can be anything, and I would have a D times D matrix with thousands of patterns stored. If my number here is higher than 2, then that's simply not possible anymore. And it's also not possible if it's the exponent. So if we have 1,000 patterns, we really have to store the 1,000 patterns. Yeah. Any questions so far? No. Okay. So the question is, of course, does it work? And here we have binary patterns, and this time so it's 4 times 6 is 24 patterns. We tried out with 24 patterns, and we retrieve Humor without any problem. Okay, so we have an extremely high storage capacity now. We retrieve the pattern. Yeah. So they also show that if we use the exponent as interaction function, that retrieval works in one update step. So we don't have to iterate anymore. It's not, so it's a probabilistic statement, but the probability that we retrieve it in one update step is very, very high. So that's good enough. But it's still not differentiable. So still not usable for our purpose. And so we had to generalize the modern Hopfield networks to continuous states. So now our patterns that we are storing and our patterns that we want to query the memory with are, they should be continuous. And it turns out that if you want to have continuous patterns, that this is the right energy function, or one energy function that delivers what we want. So here, that's the log sum exp. The log sum exp is a continuous approximation of the arc, of the maximum operator, actually. So it's just the logarithm of the sum of the exponents. So here we multiply our x's with all the x's, and we get the vector, and pointwise on this vector we apply the exponent function, and we sum over them. So if one inner product here is extremely high, for example, the log sum x would exactly just give us back this value. And we also need this quadratic term, because otherwise we just could minimize this stuff into infinity. And now, how does the update rule look like? Before I showed you that we had this update rule with the sign and the multiplication with of patterns with weight matrix. The new update rule looks like this. So here we have our stored patterns. We apply the softmax row-wise in this. No, in this case it's column-wise on this multiplication. Yeah, so that's just how that looks like. And in our paper, we can prove that, so this update rule converges to a stationary point of the energy function E. So it's either a local minimum or a saddle point. The storage capacity is exponential in dimension D, which is nice. So we keep the property of the binary network. And for well-separated patterns, the update rule retrieves patterns with one update step. So here it's the problem in the continuous domain, of course, is that in contrast to the binary or polar domain is in the binary or polar domain, you exactly know when you're done. So all entries are either 0, 1 or -1 and 1, and then you exactly know when you're done. In the continuous domain, you can probably converge indefinitely to the pattern, and so we bound it with an epsilon more or less, and and it turns out that this new update rule is actually the self-attention of the transformer network. So if we map this, if our input patterns xi are just the axes, and we map both of them with linear mappings WQ and WK, and this here with WV, and our beta is 1 over square root of dk, then it turns out that this is exactly the transformer self-attention. So without any mappings, but using it just as associative memory, here we have our images again. This time they are continuous, and we have no problem with retrieving Huma. And the retrieval, of course, is highly influenced by beta. So if beta is too small, there is just some weird averaging going on. So the higher beta is the beta it retrieves, of course, the original pattern, which also coincides with the notion of the log sum x being the max operator. So this image is a bit difficult to explain, so I hope I can do it in a few sentences. So what we looked at is if we really interpret the self-attention of transformers as Hopfield networks, in which states does such a transformer operate? So is it operating really does it really retrieve only one pattern or few patterns, or does it retrieve such averages? So what you see here is the 12 times 12 attention heads of a bird, pre-trained bird. So layer 1 up to layer 12. And we sorted them. So, okay. So per attention head, what you see is a violin plot of the distribution of the average softmax counts. So softmax count is we count the softmax activations that are necessary. So that are necessary to have 0.9 activation or more. So for example, if we look at this head, only one softmax entry is necessary in average to achieve 0.9 of the weight. So in average, this head will only retrieve one pattern. While, for example, this head will more or less operate somewhere here and retrieve some averages. So what that tells us is that here the lower layers, they are mostly averaging. And the logic probably is going on here in these layers. So here are really, that's so in terms of self-attention, it would mean, so I have attention on just a few patterns, so just a few input words, for example. And here I just gather some global information about my sentence, for example. Yeah. So that was quite interesting to us, and we just swapped out those heads with the average, and it turned out to work well. And if you swap out those heads, the performance immediately drops. Okay, so we found our associative memory that we can use, and so we went on and defined 3 layers. So the naming is a bit strange, probably, but yeah. So the first layer we just called Hopfield, the second layer we called Hopfield pooling, and the third layer we called Hopfield layer. And I'll explain what they are doing. So the layer Hopfield is just what you would also have in the self-attention, for example, in the BERT or transformer. So it associates 2 sets. Both sets are mapped with linear mappings, and also the output is mapped then. So that's the transformer self-attention. It's for point set operations or sequence to sequence, for example. So that's, yeah, it's basically the self-attention as we know it. Then the second layer is so-called Hopfield pooling layer. Here we fix this query, the query vector, and or query matrix. So it's not dependent on the input, but we learn it. And here we get our input that is mapped. For example, this could be the output of some other deep network. And what you can see here is that, for example, if we only would have a vector here, that this is a vector matrix operation. So what we would get out here is just a vector. So this layer really pools our input. And what this layer does is more or less it learns to ask the right questions. So where should I look to find the right information? So what we did, and you will see that then later in the experiments, one task was a multiple instance learning task. I don't know if you're familiar with this setting, but so it's a classification task, and your data is represented by a whole bag of instances. So in our cases, what we, for example, had was a immune repertoire classification task. So we have a lot of people, and we have the labels that say, okay, this person is immune to a certain disease or not immune to a certain disease. And what data per person we get data, and the whole we get the whole immune repertoire of this person. So per person we have about 300,000 representations. So that's some sequences that represent certain immune antigens, actually. And then by classifying, so this would be here. We mapped it beforehand, but this would be the input here. And here we learn, for example, for one person, we have 300,000 inputs here. And by multiplying this Q with this input, the network then tells us this person is immune or not. And the cool thing here is that we then can interpret which of those immune sequences is really the right one to be immune with this with regards to this specific sickness. So that is not only important for prediction, but it also gives us a great interpretability. So in the end, we could say, okay, it's exactly this sequence. We could produce this sequence. We could then incorporate it into I don't know, some vaccine or something and vaccinate people, and they would be immune in the best case. Yeah, and also this resembles a lot RNN. So probably if you go back here, if the Q's are our hidden states, for example, and we get a time series here as input as Y's, or this would be just an RNN. And also what we could learn, no, that's the next layer, I'm sorry. Yeah, and the last layer is the Hopfield layer. Here we only get the query as input, and we learn some fixed patterns here. So either we learn it or we provide it. And what we could learn here, for example, is some similarities. So we could learn some cluster centers, for example. It would be similar to, or we could learn some support vectors, things like this. Or we could even fill this matrix, we could initialize it with training data, for example. So this is actually something we want to do now in few-shot learning. We only have a few data points, and we fill them up, fill the memory up. We probably apply some learned transformation on it. But actually what we then just do is we get a new data point we've never seen before. We compare it to all the data points we have. And here, for example, the WV could be our labels. Then our output is then just the labels. Yeah, so it's similar if those VK would be, for example, let's say some similar notion like support vectors or something. Yeah, so these are the 3 layers we defined, but that's probably there are more of them. And yeah, so we tried that out on multiple data sets. So one multiple instance learning problem, or actually 2 multiple instance learning problems. One of them I already explained a bit. Then we tried it out on a small classification task and on a drug design problem. So here is the immune repertoire classification problem I already talked about. And so this DeepRC is our Hopfield network. It was just, so it got its own paper. And it was accepted before our original Hopfield Networks paper. Yeah, but and we outperformed here all other methods. Just so a lot of methods have problems with the large number of instances. So here per person you have 300,000 instances, and many methods just can't cope with that or are extremely slow. And so our competition here were support vector machines and k-nearest neighbors. And luckily we could outperform them. The next MIL benchmark data, the next MIL data set was a benchmark data set that's elephant, fox, tiger. So here the class is represented by just batches of images. So you for one data sample is like in the vision transformer, it's just a batch of images, for example, of elephants or whatever. And there is also the breast cancer classification task from the USCP dataset. It's similar. And also here we performed quite well, actually. And what I think is very interesting is the performance on small data sets. So traditionally, we know that deep learning doesn't really perform well when we don't have enough data. So we concentrated on the 75 small data sets in the UCI data sets. So the UCI is, I don't know if you know it, but it's a collection of some actually quite simple data sets. And we concentrated on the 75 small data sets with less than 1,000 samples. And we compared ourselves with SVMs and random forests and so on. And well, so it's a bit of a bold statement if you look at the p-value here. But at least so we report here the average rank difference. So for every task we ranked the methods, and in average we were most often Hopfield was among the best ranks. And you can see here the p-value is not the greatest, so it's not significant. But for 10 data sets, at least, we got new state-of-the-art results. And I think it's cool that we have now a method where we can have similar performances with deep learning, like with SVMs or SNNs. Specifically, if you think about problems, so it's common now that you have some really big pre-trained networks, like BERT, or also now with CLIP, you have a big, very general vision network that is trained, for example. So the perception task more or less is done. And now what would be cool is to have a small network that really adapts very fast, and that is not trained with a lot of data, but only with a few samples. And yeah, so this will be the next direction, also a bit with respect to the Anyline project I'm on. So this will go into the direction of few-shot learning and so on. So we want to use that. And there is a drug design data set. So I won't go into details here, but yeah, we also performed reasonably well here with respect to methods like SVMs, XGBoost, and so on. And it was also very nice to see that we, Yes, I think it's the end of my talk. So here are some resources. We have a blog about the Hopfield layers. Our software is on GitHub, so we implemented those layers in GitHub. The implementation is a bit, so our first thought was we want to implement it based on the PyTorch implementation of transformers, which in the end wasn't a very good decision. So probably you're confused with all the parameters at the beginning. We are thinking about a lightweight version now. But if you have questions, you can, if you want to use it, you can ask us anytime. This is the link to our paper, and there is even a video of Yannick Kilcher on YouTube. It's concerned with an older version, so it's a bit different. But yeah, it's still, I think, really cool. Yeah, and those are the people who worked on the paper. Thank you for your attention. So if you have any questions, please ask.
Thank you so much for your presentation. Super interesting. I think this is a great time while we have you here for any questions that might come up. Don't be shy. We still have some time left over, so please ask away. If you want to type it in the chat, I can also read it out loud, or feel free to just unmute yourself and ask any questions. So perfect time while we still have we still have about 15 minutes, 10-15 minutes if you have any questions.
So as far as I understood, one could replace GRU and the LSTM layers with Hopfield layers, right? And would there be any, could one expect any performance gain by this? And how then the training time would compare to LSTM on GRUs?
So replacing, I don't know. I don't know in terms of performance or which would be the right setting, but yes, in principle that would be possible. And actually, I don't know. So we haven't tried it out, but in principle, it's just another form, more or less, of an RNN. So that would be also very interesting to us. There is a new paper. It's called Perceiver, I think. And they are doing something very similar. I don't know if you know it, but what they also do, so instead of having a time series, they plug in always the same image, for example, and apply the attention on it and do that multiple times. So that's already very similar to this idea here. But yeah, I'm actually I can't say anything about comparison of performance or training time. So we didn't do any experiments in this regards. It's just conceptually it's possible, so to say. Yeah.
Okay, thanks.
Hi, Hubert.
Hi.
Thanks for the talk. It was a great presentation. I have a question about the classical Hopfield networks. As you said that you normally, let's say, replace this quadratic function here with some other nonlinearity. And you said that if you replace it with the exponentials, then you basically get like very high capacity. But how basically this update rule is also follows from the energy potential, as I got it. How does it work in terms of this exponential function?
The update rule, you mean?
Yep.
Yeah, that's something I didn't explain, but I think I have it somewhere on my slides. One moment. Yeah, here. So in terms of the exponential, we get this update rule. So it's the exponent of the LSE. So the exponent just cancels the log. So what we have then is we have the sum of the exponentials then. And then the update rule is this here. So it's the softmax. Yeah. So it looks already very similar. No. I'm sorry. That's not the right update rule. I don't know it by heart now. Yeah, I'm sorry. I don't know it by heart. Yeah, but it's a very simple update rule as well. I think it's similar to the softmax here. Yeah.
Yeah. Okay. Thank you.
I don't know if this was the question even.
Yeah. Basically, want to follow that.
Yeah, I'm sorry. I don't have it on the slides and I don't know it by heart. I would have to look it up. Yeah.
Okay. Thank you.
So any other additional questions? Okay, well, it seems like then that's everything. If you do have any questions afterwards, feel free to use the Meetup chat, contact Hubert directly. Again, thank you so much for the presentation today. I did record this. This will go up on our YouTube channel in our computer vision playlist. So if you would like to watch it back, it will be available probably starting end of next week. Otherwise, as always, if you have any topics you're interested in, or if you would like to give a presentation, talk about something you're really interested in, please let me know. We're really happy to have the community also give presentations, talk about things that they're interested in. So just feel free to reach out either via Meetup or via my direct email. Great, so then stay tuned. We'll have another Meetup in May, at the end of May, and I will post more about the presentation and speaker in the next month or so. Great. Thanks, everyone. Have a wonderful night. Hopefully you can celebrate the day off on Monday with some nice weather, and we will see you in May. Thanks, everyone. Have a good night.
Thank you.
Bye.
Bye.
Bye, everyone.